All right, so this is a video recorded version of Lecture 15. So in this lecture, we're starting a new chapter. We're starting on Chapter 4. So Chapter 4 is really all about taking the ideas of the Laplace transform that we learned in Chapter 3 and learning to apply it to, progressively more complex applications. All right. Now the simplest application for us is going to be the circuit, right? So in the previous class, we looked at a few different concepts. So if you were to have a resistor, okay, whose value is R, and the voltage across the resistor is V sub R, and the current through that is I sub R, right? Then we know that V sub R, okay, is simply R times the current. Now, what this means is if you were to take the Laplace transform of both sides, I'm going to get VR of S, okay, is R times IR of S. All right. So this quantity here, okay, is a constant. That's a resistor. Okay, we're assuming that it's not changing. All right. So once you wire in a resistor, it stays at the value that it's wired in. All right. So one way to also call a resistor with a new name is as an impedance, right? So the resistor is, can also be called an impedance, ZR, okay, is simply R, right? Now the ZR value is independent of frequency because the resistor, its value has no relationship with frequency, right? Impedance also is measured in ohms. Okay, and it's simply a generalization of the concept of resistance to the complex domain, right? So even though we're going to the complex domain, it's simply a real quantity, okay? The imaginary part of the impedance for a resistor is still equal to 0, all right? So now, if we were to look at an inductor is a little bit more complex, right? So if you have an inductor, which is like a coil of a wire, right? Suppose we were to denote the value across that as V sub L and the current through this as I sub L, right? Now these could be time varying quantities, right? VL of t or IL of t, right? Now what's possible is that there could be some initial current flowing through this, right? So the basic governing equation for an inductor is VL of t is L di over dt, right? So if you were to convert this to Laplace domain, we're going to get VL of S is L times, okay, the Laplace transform of a derivative. So we take S times the Laplace transform of the current, okay, minus, okay, the initial value of that current, okay, at 0 minus. All right. So if we were to look at this, okay, we get SL IL of S minus L IL of 0 minus, right? So if we were to compare this with the previous equation for the resistor, which was VR is R times the current through the resistor, right? We can sort of see that SL is sort of the quantity that's analogous to the resistance, okay? We call this the impedance for an inductor, and we denote that ZL, okay? So ZL is equal to SL, right? Now, unlike the resistance, ZL is frequency dependent, okay? Okay, and of course L is considered to be a constant. So once we have an inductor, okay, we're assuming that it just stays wired. So now if I were to take the same circuit and write that in the Laplace domain, okay, then I can basically write a diagram that kind of looks like this, and this diagram reflects this equation, all right? So everything here is in the Laplace domain. So the so the inductance here, which was L, gets replaced with SL, which is this guy here, right? And but then in series with that is this negative voltage, right? So we put a negative sign this way, okay? And this voltage is going to be L times I sub L of 0 minus. So the initial current through the inductor, which is the initial energy, right, that's stored in the inductor, is represented by this, okay? So this represents the initial condition, all right? So an inductor can have an initial store of energy, right? And it's essentially represented by this voltage source, all right? Now, there is an alternate way of doing this, right? We could have also written this equation in terms of I sub L, okay, as you see on the slide, okay, on the right hand side. You can also express this initial current as a current source, okay, that's in parallel with the inductor, okay. Anyway, so for this course, just to keep things simple and organized, we will just go with this representation, all right? We're not going to confuse ourselves with two different representations. They're perfectly equivalent, they're perfectly valid, okay? Just for our purposes, we're going to use the voltage-based representation in this course, all right? So now if you look at a capacitor in the time domain, okay, can have a representation that looks like this, okay? The voltage across that is V sub C, the value of the capacitor is C, and the current through that is I sub T, right? So the governing equation for a capacitor is I sub C, okay, is C, okay, dV by dt. So basically what this is saying is that the capacitor can have an initial charge. Charge is simply an accumulation of current, right? Electrons just go there and accumulate. Now, whenever there's a fluctuation in the charge, that's what this derivative is telling us, okay? There is going to be a current through the capacitor. So if the current is flowing into the capacitor, it's going to charge up. The voltage is going to go up. If the current is going out of the capacitor, then this voltage is going to go down because the capacitor is getting discharged. All right. So now if we convert this to the Laplace domain, I can write this as IC of S, okay, is C times the Laplace transform of this derivative, right? So this is going to be S times, okay, the Laplace transform of this voltage minus, okay, the initial value, okay, of this voltage. All right, this is the basic theorem for writing the Laplace transform of a derivative, right? So now if I expand this out a little bit, okay, this equation looks like this, right? C Vc of 0 minus, right? So now what we can do is we can solve for the voltage, okay? So I can divide throughout by SC, okay? So I can get I sub C of S divided by SC, okay, equals Vc of S minus, okay, 1 over S V sub C of 0 minus, right? In other words, Vc of S is IC of S divided by SC plus 1 over S V sub C of 0 minus, all right? So now what that's telling us is that the quantity that's analogous to resistance, okay, this is called the complex impedance of the capacitor, okay, Z sub S is this term 1 over SC, right? So, and then there is a series, a voltage in series, okay, equal to this value that is describing the initial condition. Okay, so if I were to take this and describe this in the Laplace domain, okay, I'm going to get a circuit that looks like this, right? So I'm going to have an impedance which is 1 over SC, and then I'm going to have a series voltage source describing the initial charge on the capacitor, which is V sub C of 0 minus divided by S. Okay, and this kind of more or less appears like a step function. It's almost like there was a step function with an initial voltage that was applied to this. Okay, so if this slide on your left basically summarizes the three different cases that we just went over. If you look at the resistor, okay, it is a constant and its complex impedance is simply R. If you look at a capacitor, its complex impedance is 1 over SC, and this is frequency dependent. So as the frequency increases, okay, the impedance will decrease. On the other hand, for the inductor, as the frequency increases, the complex impedance will increase. Okay, the resistor, the inductor will become like an open circuit at infinite frequency, whereas the capacitor will become like a short circuit at infinite frequency. All right. Now, as we talked about in the previous class, a voltage source, okay, like a battery, will appear for all practical purposes like a step function to us from a circuit analysis standpoint. So it's like V0, which is the voltage of the battery, divided by S. Okay. Now, if there is one thing that you really need to always remember, it's the fact that there is a negative, okay, initial voltage for the inductor. In other words, this initial voltage on the inductor, which is also called the reactive voltage, by the way, okay, is backwards compared to, okay, what we have for the capacitor. So let's work through a few examples. All right. So if you take a look at the circuit that you have on the left-hand side, okay, what we want to do is we want to find the current through this circuit, right? So let's look at all the parts of the circuit that are to the left of this red dotted line, right? So if you look at it, all we have is a battery, okay, with an initial voltage, okay, its polarity looks like this. It has an initial voltage of 1.6 volts, okay, and there is a switch, and that switch is flipped at time t equal to 0. What that means is that for all practical purposes, we are applying a step function, and the Laplace transform of the step function is 1.6 divided by S, right? And then, if you look at the parts of the circuit that are to the right-hand side of this vertical dotted line on your left, right, you have the resistor. So the value of the resistor is 4 ohms. So its impedance is also simply 4, right, 4 ohms. And then, if you look at the capacitor, right, in the Laplace domain, so we are basically drawing everything in the Laplace domain here, okay, by the way. So if you look at the Laplace domain, you have a capacitor whose value C is 0.1 farad. Okay, that's a pretty hefty capacitor actually. Its impedance is going to be 1 over SC, which is basically 1 over S times 0.1, right? Okay, and this whole thing is going to be in units of ohms, right? And then this capacitor has an initial voltage of 0.4 volts. So we have to have an initial, voltage source here, okay, whose value is going to be 0.4 volts divided by S. Okay, remember this appears kind of like a step function for all intents and purposes. And then when we get to the inductor, okay, the inductor's value L is 0.4 Henry. So its inductance is going to be SL, okay, which is going to be S times 0.4, okay. And then it's going to have a voltage source in series with that. But remember, this guy is going to be backwards, right? So it's going to be wired kind of like that, right? And the initial current through this is 0 amps. So this guy is going to be 0 volts, right? So we don't have to, in this example, worry about the initial current in the capacitor because it just happened to be 0 for this particular example, right? So now we have a circuit diagram that mimics the circuit diagram that we were given, but it's in the Laplace domain, and it includes all the initial conditions, okay? So this is a very general representation of our circuit, okay? And now all we have to do is to simply solve it. So if the current through this is given by Is, okay? Is is simply given by the total voltage, which is 1.6 divided by S, minus, okay, 0.4 divided by S, okay, divided by the total impedance along this path. So this is going to be 4 for the resistor, plus 1 over SC, okay, which is basically 1 over S times 0.1, which is basically 10 divided by S. Okay, so I'm going to write that as 10 divided by S, plus, okay, 0.4 S, okay, which is the impedance associated with the inductor, right? So I can write this as 0.4, okay, S basically. So now we can simplify this, okay? So the numerator becomes 1.6 minus 1.4 is simply 1.2 divided by S, okay? And the denominator is basically 4 plus 10 over S, okay, plus 0.4, right? So I can write that as 4S divided by 10, okay? So this is equal to 1.4 divided by 4S plus 10 plus 4S squared divided by 10. Now if I multiply the numerator and denominator by 10, I get 12 divided by 4S squared, okay, plus 40S, okay, plus 100. Okay, now I can multiply, divide throughout by 4. That gives me 3 divided by S squared plus 10S plus 25. This is equal to 3 divided by S plus 5 squared. Okay. Now I can calculate the inverse Laplace transform of this. Okay, it's going to be 3. Okay, and since this is 1 over S plus 5 squared, you got S plus 5, right? So it is frequency shifted, so it's going to be e to the minus 5t. Okay, and this is going to be 1 over S squared. Okay, so it's going to be t ut. All right, so we can calculate the inverse Laplace transform, and we can calculate the current through this circuit, okay, quite easily. So our next step is going to, we're going to take a look at another example, all right, and continue along this path, right? So for our next example, we are given the circuit that you see on the top part of the slide, and we are given an input voltage that's kind of interesting, right? So it looks like this. So this voltage was 15 volts forever, right? Going back into infinity, okay? And then it abruptly takes a dive, okay? And then it comes kind of springing back, okay? And the equation that describes that is 15 times 1 minus e to the minus 2t, okay, volts. So basically this voltage it's like a glitch, okay? We can think of this waveform as kind of a glitch, and this is our V input, okay? So in order to solve this circuit, we need to do two things. First of all, we need to analyze this part and determine, okay, the initial conditions. And then basically the initial conditions at 0 minus, right? T equals 0 minus. And then we need to start with these initial conditions and we need to apply, okay, the this exponential part of the input, okay, with the conditions starting at 0 minus, and that will give us, okay, the conditions of the circuit at any point t. Okay, so we need to work on this problem in two parts. Okay, so let's work on the first part. So the first part is to find the initial conditions. So if you think about it, right, we've got a steady input for an infinite duration of time, right? And a steady input like that means that all transients would have completely died out. There is, in other words, nothing changing in the circuit, right? So if what we can do is we can rewrite our circuit with that thought in mind. So all the currents would have settled to their final values. There are going to be no fluctuations, and all voltages would have settled to their final values, right? And there are going to be no fluctuations. So under these kinds of steady conditions, right, let's start to rewrite this circuit. So we're going to have an input voltage, okay? And this guy is going to be 15 volts, right? Right? And then, okay, and then we have this resistor, okay, which is 2 ohms, all right? And then we have a resistor here, which is 5 ohms, okay? But then if you look at the capacitor, right, there is not going to be any current flowing through it, okay? So for all practical purposes, this capacitor appears as an open circuit, okay? And it's going to have some initial voltage across it, okay? We need to figure out what that is. And then if you look at the rest of the circuit here, right, there is an inductor here, remember? So we had a 2 Henry inductor, but if the current is flowing steadily through that, right, it appears for all practical purposes like a short circuit, right? So whereas this guy appears like an open circuit, the inductor appears like a short circuit, okay? And then the output goes to a 3 ohm resistor across this like that, okay? And then the output voltage is measured here. All right. So the voltage, all voltages at 0 minus, right? So this is basically our V out at 0 minus. That's what this guy is, right? So our job is now to figure out what these voltages and currents are, right? So obviously there's not going to be any current flowing through this, right? So all the current is going to flow like that, okay? So let's call that current I, okay? That current, which is basically I of 0 minus, right? I of 0 minus is going to be just a very simple thing, okay? It's going to be basically 15 volts divided by the total resistance along this path, which is 2 plus 3, which is 5, okay? Which is going to be 3 amps. All right? So the initial conditions are now very clear, right? So if you look at the voltage across this is going to be 15 volts minus 3 amps times 2 ohms, right? Which is 6 volts. So 15 minus 6 is going to be 9 volts, right? So the VC of 0 minus is going to be equal to 9 volts, okay? And then the initial current through the inductor is 3 amps, like we just discussed, and the output voltage, okay, is going to be 3 amps times 3 ohms, right? So the output voltage is, initial voltage is going to be 9 volts, right? 3 times 3. So now we have the initial conditions for this circuit. So let's get to part 2. So in part 2, what we're going to do is we're going to apply these initial conditions, okay, this one and this one, and redraw the original circuit in the Laplace domain. That's our job, right? So let's go at it. All right. So let's go back and look at our original circuit, right? So in the original circuit, we had a voltage source that looked like that, right? And it was Vn of t, right? So we're going to find the Laplace transform of the input voltage, right? So we're going to, this is going to become Vn, capital Vn of S, right? So we're going to do that, and then we're going to get a resistor. Now the resistor goes unchanged into the Laplace domain, so it's just going to be a 2 here, right? And then I'm going to have another resistor here, R2. Okay, this is going to be 5 ohms, and that's going to stay the same. And then I'm going to have a capacitor here, which is 0.1 farad. So this is going to become 1 over 0.1 S, right, in terms of impedance. And then there's going to be a series voltage across it, which is what we just calculated, right? And what we just calculated was going to be 9 volts, right? And we're going to write that as 9 divided by S, right? Remember, this is the formula for a capacitor's initial condition, right? And then the next thing we're going to do is we're going to go back and look at this inductor, which was 2 Henry. So this is going to become 2S, right? It's SL, so this is going to become that. And then we're going to put a sort of a voltage source, which is wired backwards. So we're going to have a minus sign here and a plus sign here, right? And that's going to be L times the initial current. The initial current was 3 amps, as we just found, right? And the inductor is 2, right? So this initial voltage is going to be 6, right? 6 volts. And then in the original circuit, right, we had a 3 ohm resistor here, okay, and that's going to go there unchanged, just like that. And this is going to be our output voltage, plus, minus, like that, and we're going to write this as V out of S, right? So when we are talking about this guy, okay, we're now talking about this part, okay, the rising part, which is like 15 times 1 minus e to the minus 2t, okay, ut obviously, right? We should have a ut there in the slide. So the Laplace transform of that, so the Laplace transform of Vn is going to be 15 times the Laplace transform of 1 ut, which is 1 over s, minus the Laplace transform e to the minus 2t ut, which is 1 over the frequency shifted version of the thing. So it's going to be s plus 2, okay, and that's going to be the Laplace transform of our input voltage, right? So this is a circuit with 2 meshes, right? So so this is the first part of the thing, and there's a second part of the thing. Suppose we call this current I1, we call this current I2, okay? Now we need to write down these mesh currents for this circuit. All right, I hope you're following along, and let's get to writing down the mesh current. So again, this circuit here, okay, which is sort of our part 2, okay, contains all the information from the early part of the circuit, right, where when the voltage was a fixed, 15 volts, all the way from minus infinity to 0. It contains that information in the form of these 2 initial conditions. It's encoded in that, okay? And then it also contains the input that has been applied, okay, and that's part of this formula here, right? So all we need to do is to apply this input to this circuit and then solve for it, right? And in order to do that, we're going to first solve for the current I1 and the current I2. Now, we don't really need to solve for I1 because all we need is the output voltage. So it's enough if we simply solve for I2. Let's keep that in mind, right? So basically, let's start out by writing down the Kirchhoff's laws for this circuit, all right? So the way to do that is to first write down, okay, KVL for this part of the mesh, right? So the voltage is going to be Vn of S, okay? Let's keep going along in this direction, okay? And then I'm going to subtract, okay, 9 over S, okay? And this voltage, okay, corresponds to the current I1, okay, times, so let me write down first the sum of all the impedances, right? So I got 2 ohms here, and I got 5 ohms here, okay, plus 1 over 0.1 S, which is same as 10 over S, okay, times I1. So that's all the currents flowing in this direction. But then the current I2 is going to be flowing in the opposite direction, right, through this section of the circuit, the one between this dot and between this dot. So that's going to be like minus the sum of the impedances along this path, which is 5 ohms for this, plus 10 over S for this guy, okay, so this is like 10 over S, okay, times I2, right? So this is our first KVL. Now we're going to write a KVL for this part of the mesh, right? So in terms of voltages, we're going to have 9 over S for this, and then we're going to add the 6 volts here for this guy. And currents wise, okay, now for this part, if we use in the clockwise as a sense for this circuit, right, the current from I1 is going to be essentially going in the opposite direction, right? So I'm going to write the voltages for that, okay, as first the sum of the impedance along this path, which is 5 plus 10 over S times I1, okay, and then I'm going to write down plus the sum of the impedances along this mesh, okay, which starts off with, okay, say 10 over S plus 5 plus 2S, okay, plus 3 ohms, okay, this whole thing times I2. All right, so now we have a pair of simultaneous linear equations that need to be solved in order to calculate the currents. So first of all, actually let me just go over sort of the messy version of the solution, okay, on the slide, right? So one way to do that. Now remember, we are only interested in solving for the current I2 because 3 times I2 is going to be the output voltage, right? That's all we need. We don't need to explicitly solve for I1. All we need to do is to eliminate I1 between these two equations, right? So I can solve for I1 from the first one and plug it into the second and then solve for I2, right? So if we were to do that, you know, it's a lot of algebra, as you can see on the screen, right? It continues on to the second screen, and at the bottom right hand side we get the final answer, right? It's a ratio of 2 polynomials, a second order polynomial on the top divided by a third order polynomial on the denominator, right? So we get a formula for the current I2 that looks like that, right? So before we try to solve this, I thought I'll go over what I consider to be a much cleaner solution, right? Let's go over a much cleaner way of solving simultaneous equations, right? So let me put this note aside for a little while, and let's talk about what's known as Cramer's rule, right? So Kramer's rule is something you may have encountered in your math class, right? So basically, given two differential equations, say ax plus by, okay, equal e, and cx plus dy equals f, right? What we first do is we form what is called the determinant, right? So we start off by forming the determinant for the unknowns, the x and the y, right? We call that delta. So delta is the determinant, and that's composed of these four numbers, right? A, B, C, and D, right? And the determinant basically expands out into the following formula: A times D, okay, minus C times B, right? Now, one of the important things is we want to make sure that this is not equal to 0. Okay, this should be non-zero, right? Because if this is 0, then we probably don't have a good solution to this simultaneous pair of equations, right? Now, let's try to form another determinant. Let's call that delta x. Now, for delta x, what we do is that the parts of the determinant that correspond to x get replaced with e and f, right? The terms from the output. And the other terms stay the same. The b and d stay the same, right? So this expands out again as ed minus bf, right? Now, if I have this, then the solution to x is given by delta x divided by delta, which is ed minus bf divided by ad minus cb, okay, provided, okay, delta, okay, is not equal to 0. Okay, if it's equal to 0, then this doesn't work, right? Now, if I want to solve for y, I can get a very direct solution to that by doing the same exact thing, except I stick the e and f where the y used to be, right? So I stick e and f here, and I keep the a and c from before, and I get af minus ec, right? So what that gives me is a way to solve for y, right? Which is delta y divided by delta, which is equal to af minus ec divided by delta, which is ad minus cb, right? And again, provided delta is not equal to 0, right? Because it doesn't make sense to divide by 0. That's an important thing to check for. So what we can do is we can use Kramer's rule to solve our pair of equations, right? Now, before we do that, I think it makes sense to do a little bit of cleanup, don't you think? So let's do that, right? So let's do some cleanup. Okay. So for the first equation, it's going to be Vn minus 9 divided by S, okay, equals, okay, 7 plus 10 over S times I1 plus, minus 5 plus 10 over S times I2. Then the second equation is going to be 9 over S plus 6 equals minus 5 plus 10 over S I1 plus, okay, 10 over S plus 2S plus 8 times I2, right? Now I can further clean this up by multiplying throughout by S. Okay, so let me take a red pen to do that, just so you can see my work. So I can put an S here. I can knock out this S. I can stick an S here, knock out this S, stick an S here, knock out this S, knock out this S, stick an S here, stick an S here, knock out this guy, knock out this guy, make this squared, and write an S. Okay, so now we have a set of equations that are, a little bit cleaner. So let me write that down in the cleaned up mode, in a clean way. Okay, I think that's always a good idea. So let me do that in the format of this Kramer's rule. All right, so when we do that, we get I1 times, okay, 7s plus 10, okay, minus I2 times 5s plus 10 equal to s v in minus 9, and then minus I1 times 5s plus 10 plus I2 times 8s plus 2s squared plus 10. Okay, where did I get 10 here? Should be 8. No, it's correct. So it's I2 times 8s plus 2s squared plus 10 equals 9 plus 6s, right? So my determinant delta is going to look like this, right? It's going to be these four terms, right? 7s plus 10, okay, minus 5s plus 10, and minus 5s plus 10, okay, then 2s squared plus 8s plus 10, okay? So I can expand this out, okay, as 7s plus 10 times 2s squared plus 8s plus 10, okay, this one here, minus the product of these two, right, minus 5s plus 10 squared, right? So this is going to be a little bit of a messy expansion, all right? So let's see how it goes. So this is going to go as 7s times 2s squared, so that's going to be 14s cubed, okay, plus 20s squared plus squared plus 80s, okay, plus oh man, this is getting messy. So anyway, if you expand all this out, okay, the final answer turns out to be 14s cubed plus 51s squared, okay, plus 50s. Now in doing this, right, I think you have to be very careful in how we write our 5s and our s's, right, so we don't mix them up. That's one of the things to keep in mind as we do this handwritten work, right? So this is s is common, okay, so I can take out 14s squared plus 51s plus 50, right? This is equal to delta. So now what we can do is that we can now replace, we want to solve for I2, right? So if you want to solve for delta of I2, okay, then what we do is we just need to replace these two columns with the input columns, right? So 7s plus 10 and minus 5s plus 10, and then we put SV in minus 9 here, and then we put 9 plus 6s here, right? So again, if we expand this out, okay, and work through the algebra, we get 42s squared plus 78s plus s times 5s plus 10 Vn. Okay, so now if I divide, so my I2 is going to be delta of I2 divided by delta, right? So if we do that, then we get the final answer that's seen on the slide on your left, right? Which is 42s plus 78 plus 5 times s plus 2 and so on. Now, if we actually plug in the Laplace transform for Vn, right? Remember Vn was what? 15. So my Vn was 15 times 1 over s minus 1 over s plus 2, right? So this is s times s plus 2 in the denominator, 15 in the numerator, s plus 2 minus s which is just 2. So this is going to be 30 divided by s times s plus 2, right? So we can now plug in V in as well, and we can solve for the final current, okay, which is I2 is given by 42s squared plus 78s plus 150 divided by s times 14s squared plus 51s plus 50, right? So this is going to be a final answer for the current I2. And then if we do the partial fraction on that, right? So this gives me a pole that looks like 1 over s times some constant, right? And this is going to give me a pair of poles, okay? And one of them is at, and the roots of this equation turn out to be minus 1.82 plus or minus j 0.5, right? So if we plug in these roots, okay, I'm going to get a term of the form a2 divided by s plus 1.82, okay, plus j 0.5 plus a3 times 1 over s plus 1.82 minus j, right? So this gives us a form for the current I2 of t in the time domain, okay, that looks like, okay, 3 plus 10.64 e to the minus 1.82 t, okay, cosine. So basically the cosine comes from combining these two terms, right? Now remember, A2 and A3 are going to have a special relationship. A2 and A3 are going to be complex conjugates of each other, right? So if we combine these two terms, we can combine them into a single cosine term, minus 0.5 t, okay, plus 90 degrees, okay, ut. So basically the V out of t is going to be 3 times I2. So using the Laplace transform, we ran into messy algebra, so this is not going to be uncommon, right? We have to be careful, and somehow we need to muddle our way through that. But the bottom line is that we managed to take a complex situation, okay, and this is our original situation, right? We're given a complicated input, like a glitch, that was applied to a complicated circuit, okay, that had, let me go back to that, let me flip back to that circuit, okay. This was a circuit that was given to us, okay. It has quite a few, it's got 2 different meshes and so on. So we were able to then actually calculate everything in a very systematic manner, right? And we were actually able to get a clear answer, okay, in the time domain out of this. If we had to do this directly in the time domain without the aid of Laplace transforms, that would have been a lot harder, okay? It would have taken us a lot longer to get to that, and we would have made many more mistakes along the way. All right, so let's look at another example. All right, by the way, before we get much further, it's helpful to think a little bit about what happens to the behavior of this circuit, right? In other words, what happens to V out, okay, as the frequency changes, right? So let's think that through, right? So V out, okay, of S is 3 times, okay, 42S plus 78 plus 5S plus 10 Vn divided by 14S squared plus 51S plus 50, right? And we also had plugged in this Vn, and we had a value for that, right? I think on the previous slide here, right? So this is the formula for that, right? So basically this is 3 times 42s squared plus 78s plus 150 divided by 14s times s squared plus 51s divided by 14 plus 50 divided by 14. Okay, so what we can now do is we can start to think about what happens at very low frequencies and at very high frequencies, right? So when you look at very high frequencies, right, what's going to happen is that the numerator is going to be dominated by the highest order term, right? So as s tends to infinity, okay, this ratio is going to look more and more like 3 times 42s squared, okay, and the denominator is going to be dominated by this cubic term. This is going to be 14s cubed, right? So this is going to become, 3 times 42 divided by 14, okay, s. Now s is in the denominator, right? So as s tends to infinity, this whole thing will start to tend towards 0. What that means is that at very high frequencies, okay, the output voltage is going to be tiny. That's what it really means, right? So if you were to plot the magnitude of this complex voltage, okay, you'll see that it becomes a very small term tending towards 0, right? Whereas at low frequencies, okay, it's going to, so as s tends to 0, right, the numerator, okay, is going to appear more and more like 3 times, okay, 78, okay. Sorry, 78 is going to go away. So 3 times, this term will go away, this term will go away, it's going to be 150, okay, divided by 14s. This is problematic, all right, and then this is going to become s squared is 0, 51s over 14 is 0, and then it's going to be 15 over 14, right? So this is also, going to start to blow up on us as s becomes very, very small, right? So we can also now look at the phase in a similar manner, right? So if you look at this term here, right, the phase is going to tend towards minus 90 degrees, right? Whereas as s tends to 0, the phase, okay, is going to tend towards 0 degrees, right? So we can get a feel for how this circuit behaves, okay, as the frequency varies, right? We'll talk more about that in the next chapter. Now, for the same circuit, if we were to change the input, right, and this is an interesting input. It's kind of like turning on the AC power, right? So if you look at the time from minus infinity, okay, all the way to 0, okay, this was at DC 15 volts, just like what we had in the previous example, right? But after this, okay, we are turning on a sinusoid. Okay, this sinusoid is 15 plus 20 times sine 4t, right? So this is a sinusoid with omega 0, okay, equal to 4, right? And the amplitude is 20. So at its peak, okay, sine is going to become plus 1, so these two numbers will add up. So the highest value is going to be at 34. At its trough, okay, this sine is going to become minus 1, so this is going to become 15 minus 20, so this part is going to become minus 5 volts, right? So this voltage is going to vary between minus 5 and plus 35 volts, right? So it's a sinusoid. So what we can do is we can reuse the same formula that we had before. All we need to do is to change V in, right? Because the initial condition is the same as before, right? So the circuit solution is the same. We just had to plug in the new value of V in, right? So the new value of V in, okay, is basically the Laplace transform of this guy, right? So the Laplace transform of 15 is going to become 15 over s, okay? The Laplace transform of 20 sine 4t is going to become 20 omega, okay, divided by s squared plus omega squared, okay, where omega, or rather omega naught, okay, is equal to 4, right? So this is going to become 15 divided by s plus 20 omega naught divided by, so omega naught is 4, so it's going to 20 times 4, which is 80, divided by s squared plus 4 squared, which is 16, right? So again, we can plug in this value of Vn into the formula that we had before, okay, which is what you have on the left-hand side here. And then that gives us the current value, and then we can take 3 times the current value. That gives us the output voltage, and then we can solve for the output voltage in that manner, right? So I will skip over the nitty-gritty of actually working through that algebra, right? But it's in the book, right? You can take a look at that. It's example 4-2. But let's take a look at the output and see if we can do a little interpretation of the output, right? So if you look at the output, it's got two sets of terms, right? So the V output for this case, right, is basically 9, which is like a steady state term, plus 5 times cosine of 4t minus 157 degrees, okay, plus 4.73 e to the minus 1.82 t times cosine of 0.5 t, okay, minus 14 degrees, and this whole thing ut, right? So if you think about the output, right, there is a steady state value which is 9 volts, right? It's kind of like a DC value, right? But then we have a non-decaying sinusoid, right? i.e., this is a part of the steady state solution. So in the steady state, since the input is oscillating forever, okay, the output is also keeping on oscillate forever. And just because this is an LTI system, we know that a sinusoid at frequency omega naught equal to 4 will produce an output which is also a sinusoid at omega naught equal to 4, right? So in other words, this is part of the forced output, right? So this is also a steady state non-decaying, okay, oscillation. Then there is a third term which has the exponential e to the minus 1.82, right? So this is going to be a decaying transient signal, right? So if you look at a plot of the output voltage, right, it basically initially starts out with a bit of a jolt like that, and then eventually settles down as this transient, the oscillatory transient dies out, right? The output settles into this term plus this term. So these two terms together form the steady state oscillatory output, whereas this is like a transient that just comes from switching on that input, okay, at time t equal to 0. So the moral of the story is that the Laplace transform is capable of describing a lot of, very interesting transient behaviors of circuits. Now, if these transient behaviors are not designed properly, okay, components can blow up, right? So a big part of engineering is to make sure that our circuits and systems, last a long time, right? You don't want a circuit controlling an airplane, okay, dying on you mid-flight or something like that. So we want to make them reliable. So one part of that reliability has to do with taking care of the transients, right? In this case, the transient dies nicely and quickly, right? And the omega for this is nothing to do with the input, right? So this corresponds to the modes, right? So these values are are coming from the modes of the circuit rather than the forcing, which is the input, right? So since the forcing in this case is oscillatory, right? We know for LTI systems that the forced output will also be oscillatory at the same exact frequency. Okay, so this is pretty clean except for this little transient part, and we have to make sure that this is well behaved, right? It dies off quickly and nicely and doesn't blow any parts. So let's look at the next example here. We have a circuit with a switch. Now in this case, what's happening is that this switch is short-circuiting resistor R2 at time t equal to 0, right? So one way to think about this is, okay, let's go about doing the two-part solution, right? So for the first part, what we need to do is to first understand the circuit in steady state. So we got the voltage source, okay, which is 24 volts, okay, and then we have a resistor, 4 ohms, and then we have the resistor 8 ohms, and then we have this guy here, okay, L is 2 Henry, and this is 12 ohms, okay, and there's a capacitor sitting across that, right, 0.2 farad. So this is the initial condition, okay, before the switch was flipped, okay. So the switch is still open, right, like that. So nothing has happened. So now we can solve this circuit in order to calculate this current. Okay, we are asked to calculate the IL. Okay, that's the desired output for this circuit, right? So in steady state, okay, there is no reactive voltage across the inductor, right? Because it's L di by dt, right? So di by dt is going to be 0, so there's going to be no this thing. So the inductor basically behaves like a short circuit. Okay, so this is going to become like that. This is going to be 12 ohms. Okay, and then if you look at the capacitor, there's going to be no current through it. There's no dV by dt across it, so there's going to be no current through that, right? So this guy is going to behave like an open circuit, like that. Okay, but this 8 ohm resistor is going to be there, and then this 4 ohm guy is going to be there, and this 24 volt resistor is going to be there. It's going to be like that. So now the initial current like this is going to be basically 24 volts, okay, divided by, is going to be 24 volts divided by the sums of these resistors, right? 8 plus 4 is 12, plus 12, that's going to be 24, so this is going to be 1 amp, right? Now, when we short circuit the resistor, this 8 ohm guy suddenly goes away, right? So let's see if we can rewrite this circuit, okay, without the 8 ohm resistor. So the 8 ohm resistor is short circuited, it goes away, but the 4 ohm resistor is still there, right? The battery is still there, right? It's 24 volts, so in the Laplace domain it becomes 24 divided by S, okay? And then this resistor goes away because of the switch that was flipped, and this inductor, okay, was 2 Henry, so it becomes 2S in the Laplace domain. But in series with that, we had to stick a voltage source, which is kind of pointed backwards. Remember, it's an inductor, so it's pointed backwards, okay? And this is going to be equal to IL times 2, right? 2 is the inductance, 2 Henry, and the initial current was 1, so this is going to be 2 volts, right? So like that. And then you still have the 12 volt resistor, okay, and then the capacitor becomes, okay, it's 0.2 farad, so 1 over S times 0.2, okay, and 0.2 is same as 1/5, so it's like 5 divided by S. And then this guy is going to have a voltage in series that corresponds to the initial voltage across this whole space, right? And this initial voltage is essentially 12 volts, right? Because there was no current flowing across this, right? So in steady state, right? So it's going to be 24 volts minus this current here, okay, times 4 ohms plus 8 ohms, right? So that is going to be 12 volts, right? So this is going to be 12 volt. But then we're going to divide that by S, all right? Because it's a capacitor's initial voltage. So now we need to solve this for IL, right? We're going to do it in the Laplace domain, so I'm going to put a capital IL here, right, of S. So we can solve for this using a variety of ways, because the voltage here is common, right? So if that unknown voltage here is V, the sum of this current plus this current plus this current is going to be 0. That's one way to solve for this. You can solve it however you want, but basically in the end, or you can solve it as a set of two meshes. You can solve for I1, okay, and then I2, okay, and that's how you can get at this current IL as well. Anyway, so however you choose to solve it, okay, we can solve for IL, and the answer, turns out to be like this, right? So we can now Laplace transform this. Or the inverse Laplace transform this to the time domain, and we can get 1.5 ut minus 0.76 e to the minus 1.85, okay, t ut, okay, I'm going to put ut common outside, plus 0.26 times e to the minus 5.4 t ut, okay, I put u of t common, all these guys like that. So now in solving these circuits, okay, you can use any trick that you've learned in the circuits class. And let me review one of the standard tricks that I've always found useful. It's the voltage divider. So if I have a voltage V1, right, and I have two resistors, say R1 and R2, okay, the voltage across R2, okay, is going to be R2 divided by R1 plus R2 times V1, and the voltage across R1 is going to be R1 divided by R1 plus R2 times V1, right? Now in the Laplace domain, the same formula also works, right? So if you had a Z1 here and a Z2 here, okay, then the same formulas work like in the case of the resistors, okay? So the voltage across R2 is going to be Z2 divided by Z1 plus Z2 times V1, and the voltage across R1 is going to be Z1 divided by Z1 plus Z2 times V1, right? So in other words, the voltage divider formula also works in the with the impedances. So we can use this now to reapproach our RC circuit example, a good old circuit example that keeps coming back at us all the time. Okay, and so we got the RC circuit like that. So I can directly go at it in the Laplace domain. So I'm going to write this as 1 over SC, right? And my Vn was a pulse, right? So this was a pulse that started off at 1, so it was like u of t minus u of t minus 1, right? So in the Laplace domain, I can write my Vn of s as 1 over s minus 1 over, okay, so s times the delay, right? E to the minus s times 1, right? So this is 1 minus e to the minus s divided by s, right? Now for the voltage output, okay, I can use the voltage divider formula. So I can write 1 over SC divided by R plus 1 over SC times the input voltage, right? So this is equal to 1 over, okay, I multiply the numerator and denominator by SC, right? So I get SCR plus 1, right? Vn of S. So my output is going to be, right, now my RC value for this circuit is going to be, so RC is going to be 0.5 million ohms, mega ohms, times 1 microfarad, in other words 1 millionth of a farad, right? So this is going to be equal to 0.5, right? Now 1 over RC is going to be equal to 2, right? So I'm going to get 1 over SCR, which is S divided by 2, okay, plus 1, and times Vn of S, which is 1 minus e to the minus S divided by S, okay? So this is given by 2 divided by S times S plus 2, okay, times 1 minus e to the minus S. So we can now inverse Laplace transform this, okay, much more easily, right? So first let me start out by finding the partial fractions for 2 divided by S times S plus 2, right? So this is going to be given by some number A1 times S plus some number A2 times S plus 2, right? Now in order to calculate A1, I'm going to multiply throughout by S and set S equal to 0, right? So now, and then this term will basically go away. So if I multiply this by S and set S equal to 0, okay, I get 2 divided by, okay, S is gone, so it's going to be 0 plus 2, so this is going to be 1. Then for A2, I'm going to multiply this throughout by S plus 2 and set S equal to minus 2, right? And when I do that, I get 2 divided by minus 2 times, okay, and again this term is not going to be there, so this is going to be minus 1, right? So my V out of S is going to be 1 over S, okay, minus 1 over S plus 2, okay, and this whole thing times 1 minus e to the minus S. Okay, so if I expand this out, this is going to give me, right, 1 over S minus 1 over S plus 2 minus e to the minus S over S plus e to the minus S divided by S plus 2. So now I can inverse Laplace transform this one term at a time. So 1 over S is going to be just ut. Okay, this is going to be e to the minus 2t ut minus, okay, there's a delay here, right? So I'm going to just take ut and delay that by 1, right? So this is going to give me ut minus 1 plus this is going to be a delay of a frequency shifted version. So I'm going to take e to the minus 2t ut and delay that, right? So we're going to get e to the minus 2t minus 1 u of t minus 1, right? So this is my final answer, right? So this is much easier than what we did before, right? So this is 1 minus e to the minus 2t times ut, okay, minus 1 minus e to the minus 2t minus 1 u of t minus 1. Okay. But we got to the answer much easier than before, and when you plot this out, you get this nice, beautiful shark fin kind of pattern, right, that we got before. So the RC circuit has become much easier to work with, okay, in the Laplace domain. And we can sort of see the power of the Laplace domain in this example. Earlier we had to write down a differential equation, come up with a way to solve the differential equation, and then, integrate our way, apply all the initial conditions, and so on and so forth. And in the end, we came up with a complicated answer. But here we could get to the answer much more quickly, right? So to summarize, the Laplace transform gives us a way to analyze very complicated circuits with complicated initial conditions and complicated inputs much more easily. And the key steps to doing this is to first transform the circuit to the S domain, okay? But in order to do that, you have to do it in two parts. The first part is to find the initial conditions, and in the second part, okay, you apply the initial conditions to all the inductors and capacitors, and thereby transform the circuit to the S domain, okay? And then we transform the input to the S domain, and then we use our good old KVL and KCL. They work exactly the same in the Laplace domain. And then in the end, we can finally transform the answer to the time domain, okay? So in order to plot what it looks like. This method is very general. It applies to every kind of circuit, be it a power system that runs at a megawatt or a delicate little system that's running at a microwatt. It works exactly the same, okay? Very general. Anyway, so when you come to the next class, I want you to skip over sections 4.3 and 4.4, but I want you to study sections 4.5 and 4.6. I've also created a YouTube recording for you, okay? And here's a link for that, okay? You can also watch that YouTube description before you come to the next class. And it's going to be a fun class, I promise you. All right? We'll see you next time.